Okay. So, next part of chapter 19 dealt with solubility equilibria. I want to briefly just kind of review what we need to know about this. Okay, the first thing, we got to be able to write these KSP expressions for sparingly soluble salts. Okay, that's going to be absolutely crucial to us. Need to be able to write those KSP expressions. Now, you may remember for any slightly soluble or sparingly soluble solid, the KSP expression or ion product expression is nothing more than the equilibrium constant for the dissolution of that material. Will form aqueous ions on the right always. They are the ions which make up the salt, which is placed on the left. This is always a solid. So for calcium chloride, the equilibrium would be that. And the KSP expression would be the ion product. Calcium molarity times chloride molarity. We got to square that chloride molarity by virtue of that 2 in the stoichiometry of the reaction, okay? So this is a very, very basic skill basically for us. Everybody needs to be able to write those KSP expressions. The great thing about solubility equilibria is that the stuff on the left, the reactant's always a solid, and solids don't appear in equilibrium constant expressions, so we can just kind of forget about it and write our KSP. All right, first skill, absolutely basic. Need to know how to do that. All right. The next thing that we need to be able to do is use our KSP relationship and Rice tables to compute molar solubilities, right? So you remember the Rice tables, RICE, reaction, initial change, equilibrium. Great thing again, since that's a solid, we don't care about it. But what we're going to do in our Rice table is write the initial molarities of both our ions. We're going to make some, in this case it's plus x and plus 2x. And then we're going to have equilibrium molarities as well, okay? Now you need to be able to compute molar solubilities, which is the number of moles per liter of the solid you can get to dissolve. We need to be able to do that in two conditions, either distilled or deionized water, and the next one is when a common ion is present. And the only difference in the calculation is whether or not zeros go here and here for your initial amounts. If we are doing this in distilled water, we'd write a 0 and a 0 for our initial amounts there and there. That's for distilled water or deionized water because there's no other ions present in that case. However, if we are working this problem when a common ion is present, the situation changes. A common ion is an ion that's present in our solvent from a different source other than this reaction. The reaction here doesn't care where the ion came from. It can influence the equilibrium if it's present. So if I add some chloride from a different source, if I add some calcium from a different source, that's a common ion. And I need to account for those initial concentrations in my I row of my table, okay? That's the only difference. You work the problem exactly the same. You just have some initial concentration plus x and some initial concentration plus 2x for this ion, okay? Sometimes these numbers are 0, sometimes they're not. If it's deionized water, they're 0. If it's not, you got to put a number in here and work the problem, okay? Simple enough. Got to be able to do that, okay? The next thing, then, we got to learn is be able to predict whether precipitates will form in solution. Oops. Be able to predict whether precipitates will form in solution. How in the world can we do that? Well, typically you're given a problem, it gives you initial concentrations of ions present, and you're asked, will a precipitate form, will a precipitate not form? You're going to be given a KSP value as well in these types of problems, okay? What you need to do is compute your QSP. That's your reaction quotient. So for some generic reaction, I guess we'll just consider a specific reaction like silver chloride solid, something like that, okay? It's going to make silver plus 1, and it's going to make chloride minus 1. Now you can compute your QSP by plugging in your silver molarity and your chloride molarity into the QSP expression. And then you can compare QSP with KSP. If QSP is bigger than KSP, a precipitate forms because you have too many of the ions. If QSP, on the other hand, is less than KSP, no precipitate forms. Okay, so this is how you can basically tell. Now, when you're subbing in numbers into your QSP expression for your ion concentrations here and here, you have to make sure that those ion concentrations are after mixing, after dilution. You want those ion concentrations to represent the molarities in the final solution within which a precipitate may form. All right, but that's another type of problem. And then lastly, the last point on this slide is to understand how the pH or the presence of other ions in the solution or solvent may influence the solubility of a salt, okay? So how do other ions and or the pH? And when we say pH, what we really mean is H plus may influence the solubility, or maybe I guess OH minus could influence the solubility, depending on if we're a low pH or high pH, okay? But other ions may influence the solubility of a salt. Going back to that example I just erased, I probably shouldn't have erased it, right? But say, for instance, silver chloride solid dissolving to make silver plus 1 and chloride anion, right? If I had a secondary reaction, a different reaction, that could use up or consume either one of these ions, either silver plus 1 or chloride, if I added a reactant that could react with one or the other, as soon as some of the silver chloride dissolves, I'm going to use up that silver ion, I'm going to use up the chloride ion, and its concentration will effectively drop because that secondary reaction will consume it, it will bind it up, it will remove these ions from solution. And if that happens, if I use up one of my products, it shifts to equilibrium, right, making this stuff more soluble. So always be on the lookout for these other secondary reactions. I'll show you an example of that in one of the corresponding videos. But this is basically a summary of, I think, the things that are most important for solubility equilibrium to know for tomorrow's exam.